Good morning, Excellencies, ladies and gentlemen, welcome. Let me start by recognising UNESCO's Assistant Director General for Natural Sciences, Dr. Lidia Brito, Her Excellency, Mrs. Simona Mirella Miculescu, President of the 42nd session of UNESCO's General Conference, and the distinguished Nobel laureates in physics that we are honoured to have with us here today. Particular thanks goes out to you, our audience present here in UNESCO's main hall, the headquarters here in Paris, and of course to our global audience connected across the world online to follow this very special celebration of the International Year of Quantum Sciences and Technology. My name is Hayley Edmonds, I'm a journalist, and it is both an honour and privilege to be with you here today as we embark on a journey through one of the most exciting and transformative fields of scientific discovery, quantum science and technology. This year marks a significant milestone in the advancements of these fields, and it is with great anticipation that we gather here to explore the profound impacts they are already having and will continue to have on our world in the future. We're deeply grateful for the presence of our distinguished speakers and panelists whose expertise and, of course, passion will undoubtedly inspire us all. Alongside conferences today and tomorrow, we also have the exhibition celebrating the International Year of Quantum Science and Technology, featuring groundbreaking innovations and future possibilities. Today, let's move forward with open minds, eager to explore the frontiers of quantum science, and together, let's make this a truly memorable and impactful experience. I'd now like to invite Dr. Lidia Brito, Assistant Director General for Natural Sciences at UNESCO, to the stage for the welcome address.
Thank you very much. Good morning to all. Excellencies, honored guests, distinguished participants here and online, ladies and gentlemen. 100 years of quantum science, and there's an exhibition outside this room reminds us 100 years is just the beginning of an incredible journey. So today, we begin that journey. It is my great privilege to welcome you to the opening ceremony of the International Year of Quantum Science and Technology. Welcome to UNESCO, the home of science, your home. Excellencies, this landmark moment brings together leaders from several spheres of society. Leaders, scientists, policymakers, entrepreneurs, businesses, and visionaries from around the globe to raise public awareness of the importance of quantum science and its applications, to promote international, multilateral, and interdisciplinary scientific cooperation in quantum science and technology, and hasten the application of quantum science and technology for sustainable development. This journey of discovery, of enlightenment, progress, and shared responsibilities is also a journey that will lead us to set a global agenda for quantum science and technology. 2025 is the year for that, and with all of you and many others, we will succeed to bring its benefits to humankind and the planet. The International Year of Quantum Science and Technology underscores the role of emerging scientific fields in addressing global challenges and fostering sustainable progress, becoming a key initiative of the International Decade of Sciences for Sustainable Development. Quantum science is not only a pillar of this important international decade, it's also a scientific field of incredible potential, a transformative force that will redefine our understanding of the universe, changing existing technologies in communication and other fields, and even the way we approach the most pressing challenges of our times. Quantum science is a highly complex and rapidly evolving field, and within the broader IDSSD framework, international and interdisciplinary cooperation is essential to avoid fragmentation and to establish common frameworks, protocols, and ethical guidelines, ensuring that quantum technologies are developed in a cohesive and interoperable manner. Through international cooperation, we can also address the challenges of unequal access to resources, knowledge, and opportunities to prevent further global quantum divide. Quantum science is a cornerstone for achieving the Sustainable Development Goals, particularly in addressing climate change, energy efficiency, food security, and healthcare. With only 17% of SDG targets on track as of the 2024 SDG report, it is crucial to recognize that using quantum science and technology for sustainable development is not just about scientific advancement. It's about building a better future for humanity and the planet. By integrating quantum innovations into global sustainability efforts, we can tackle critical challenges more effectively, equitably, and efficiently. This requires collaboration, investment, and a shared commitment to use these tools for the greater good. Only when aligned with sustainable development goals can quantum science truly transform our world for the better. Allow me to take this opportunity to express our deepest gratitude to the member states, particularly Ghana and Mexico, for their leadership in the proclamation of this international year within UNESCO and the United Nations General Assembly. I also extend my sincere thanks to the American Physical Society, whose unwavering partnership has been pivotal in bringing this vision to life. Our heartfelt thanks also go to the generous donors who have supported this initiative, believing in the transformative potential of quantum science and technologies. We extend our appreciation to the members of the steering committee, subcommittees, and working groups, whose efforts have shaped this initiative with clarity and purpose. My deepest gratitude to the scientists around the world. Your commitment is our foundation. Your engagement drives the global momentum needed to bridge divides and create opportunities for all, placing science and technology as a driver for sustainable development and defending it as a public good. Excellencies, distinguished participants, as we launch the International Year of Quantum Science and Technology, let us remember that it's not just a celebration of breakthroughs. It is a moment to shape the future. Let us seize this opportunity to create a legacy of cooperation, innovation, and inclusion, ensuring that the power of quantum science benefits all. Let's start our journey. Welcome to UNESCO. Thank you.
Thank you, Dr. Lydia Bruto, for officially opening this very esteemed event. Your words have set strong foundation for our discussions today, and we are truly grateful for your valuable contribution to this very important event. Now we will hear high-level remarks from 3 speakers, starting with Her Excellency Ambassador Simona Mirela Miculescu, President of the 42nd session of the General Conference. Please join me in welcoming her on stage.
Excellence.
Excellencies, Madam ADG for Natural Sciences, distinguished Nobel laureates, scientists, experts, ladies and gentlemen in the room, and those following us online. On November 14th, 1888, as he inaugurated a few streets away the institute that bears his name, Louis Pasteur said, "Science has no country, for knowledge is humanity's heritage. It is the torch that lights up the world." In the same way as the creation of the Institut Pasteur, that was to save thousands of lives, was the result of an international subscription, the event that gathers us here today is also the fruit of joint efforts on the part of the scientific community and a number of member states: South Africa, Brazil, Egypt, Spain, Ghana, Japan, Jordan, Kuwait, Mexico, Paraguay, the Republic of Korea, Senegal, and Serbia, who put this initiative to the Executive Board in April 2023. All of these member states and those that joined them must be thanked warmly for their support. We also have some 30 scientific societies and academic institutions around the world that have also contributed to the holding of this event, following the recommendation of the General Conference of UNESCO that adopted the resolution proclaiming 2025 as the International Year of Quantum Science and Technology. The UN General Assembly has been most clear. International cooperation that is deepened in the field of quantum science and technology can contribute to achieving the Sustainable Development Goals and to improving the quality of life in the world. There is no secret. Major scientific advances in the world do not happen in isolation. Intellectual cooperation on a global scale is fundamental. This involves sharing knowledge and resources beyond borders. It also involves creating ambitious partnerships between governments, the academic world, and the private sector. In that context, the Global Decade for Science for Sustainable Development, also coordinated by UNESCO, puts forward the importance of science as a vector for collective progress and a lever for social transformation. And the initiative that we are launching here today is fully part of that move and puts scientific cooperation in the service of the common good and the resolution, or at least the toning down, of global challenges. Faced with the complexity of quantum science and technology, it is fundamental that international cooperation can overcome traditional divides. It must be based on trust and the certainty that science as a universal language can overcome all differences, economic, political, or cultural. I am delighted to see that this event has not only gathered scientists and Nobel laureates in the fields of physics, but also philosophers and researchers in human sciences. It has, by the way, gathered together 3 sectors of UNESCO: natural sciences, social and human sciences, and communication and information. And this in an inter- and pluridisciplinary approach. It clearly illustrates the role of UNESCO as a driving force for intellectual cooperation. In the line of its predecessor, the International Institute of Intellectual Cooperation, whose centenary birthday we celebrated last September. We had the privilege of discussing the future of intellectual cooperation, and one of the key recommendations of our experts that were present, especially Professor Anna Maria Cetto, whom I would also like to greet here, was the creation under the aegis of UNESCO of a global forum for intellectual cooperation. This event is, I believe, a significant step on the path to that ambition.
Ladies and gentlemen, by leading the coordination of this international year, just as it does with its normative work in the fields of ethics of the artificial intelligence or of the neurotechnology, UNESCO reaffirms its anticipatory and forward-looking mission. It enables us to shape a better future by envisioning how emerging technologies advance while ensuring their benefits reach everyone. In today's world, often divided by conflict, let me recall the role of science diplomacy, the power of science to build peace. Institutions such as the European Organization for Nuclear Research, or that we all know by the name of CERN, and the synchrotron light for experimental science and applications in the Middle East, exemplify UNESCO's leadership in creating shared interests and incentives for scientific cooperation across borders. But for this cooperation to be truly transformative, we must ensure that the access to scientific knowledge, as well as the participation in innovation and its benefits, are inclusive. As we embark on this international year of shared efforts, let us keep one question in mind. Will we allow quantum science and technology to become a field of competition and division? Or will we embrace it as a catalyst for equity and peace? Well, I urge all of us, scientists, policymakers, diplomats, business leaders, and citizens, to commit to the international intellectual cooperation. Let us invest in creating open platforms for knowledge sharing and technology transfer. Let's champion inclusivity in STEM fields. Let us believe in science. Most of all, let us believe in each other. Together only we can unlock the full potential of quantum science and technology for humanity, for knowledge, and for peace. Thank you.
Thank you, Your Excellency. Our next high-level remarks will be delivered by Dr. Anna Maria Beatriz Cetto Kramis, researcher at the Institute of Physics at UNAM. Please join me in welcoming her to the stage.
Good morning, buenos días, bonjour, distinguida presidenta.
Distinguished President of the General Conference, Simona Miculescu, Ms. Lydia Brito, representing the Director General of UNESCO, and distinguished representatives to UNESCO, distinguished participants, colleagues, guests, ladies and gentlemen. It's a great honor for me to represent the recently created Secretariat of Science, Human Sciences, Technology and Innovation of Mexico for this event that launches the International Year of Quantum Science and Technology. This is the beginning of a new era in understanding and applying the fundamental principles that rule our universe. Quantum knowledge, at its purest, amplifies our understanding of reality. It has led to extraordinary advancements in a variety of fields: computing, telecommunications, medicine, engineering, and many other fields. These advances, only a few decades ago, seemed like an impossible dream. But they are becoming reality thanks to the collective efforts of scientists, engineers, and visionaries around the world. It is fundamental to raise awareness among decision makers in all sectors of the population as to the importance of quantum science in our society, and especially to inspire younger people to become the next generation of quantum innovators. It is not unimportant to insist on the relationship between education, basic science, technology, and innovation. And a clear example of this are the semiconductors, or chips, as they are frequently known. There is no field of scientific research that does not require sensors, microprocessors, systems that are analog or digital, or electromechanical devices. Mexico, as a nation committed to science, technology and innovation, is proud to be at the forefront of this global movement. Thanks to our academic institutions, our research centers, our technological companies, we are pushing forward the development of quantum science in all fields. We are not only the witnesses of progress made in this field, we are also active players. We contribute to global progress in this field. We are also today launching in our country the commemoration of this international year with a variety of initiatives. We must highlight that the development of quantum science in Technico is consolidated through the scientific work carried out in a great variety of institutions, such as UNAM, the Center for Investigation and Advanced Research, the Polytechnic Institute, the various public centers for research, and many other laboratories and research groups, to mention but a few. One of these strategic projects of the new Science Secretariat in my country aims to strengthen the value chain of semiconductors in our country, and this will be done in a variety of fields. We need a better legislative and standard-setting framework for technology in this field. We need to promote ecosystems that will include the whole chain in development hubs. We need to provide incentives for development in the electronics of semiconductors, to create a concept, a design center for Mexican technologies and the work that we've been doing over the past 40 years, and participate in legacy chips to satisfy national demand in our electronics industries, but also in medicine and research and other fields in the country. Another important role for our institute and secretariat is the O-line project to develop compact devices for personal use, such as automotive industries. We must encourage young people to take interest in science in this field. Unfortunately, we still have much to do. The students in this field only represent 15% of the total number of students in science, technology and engineering fields. and only 4% of national graduates of all of higher education. We must think about broadening our scientific debate to ensure that our youth can participate in the development of quantum science within the next few years. This International Year of Quantum Science and Technology is a unique opportunity to strengthen international cooperation and to encourage the exchange of knowledge between nations. Science, by its very nature, is a collaborative effort that transcends borders. In Mexico, we believe that the future of quantum science will be built thanks to the participation of all. And this is why the Open Quantum Institute, among other initiatives, as proposed by over 60 different countries, represents a collaborative effort of scientific diplomacy to resolve fundamental problems of quantum mechanics and lead towards the new paradigms of technological development. This year we are celebrating not only scientific advancements, but also the potential of quantum science to promote a fairer, more equitable and more sustainable future. As we explore the mysteries of quantum physics, we are also opening new doors for international cooperation, economic development, and the improvement of the quality of life of our populations. As we begin this International Year, we commit to continue working together in cooperation with all the countries around the world to make the most of the enormous potential of quantum science and technologies for global well-being. In Mexico, we are ready to continue to contribute, to learn, and to grow together in this journey towards the future. Thank you.
Thank you, Dr. Ana Maria Biarritxeto-Kramis. Now it's my pleasure to invite His Excellency, Mr. Cephas Adjej Mensah, Director of Research, Statistics and Information Management, on behalf of the Minister for Environment, Science, Technology and Innovation of the Republic of Ghana to the stage.
Thank you very much. Thank you very much. Your Excellencies, distinguished guests, ladies and gentlemen, it's a pleasure to be here on behalf of the Honorable Minister for Environment, Science, Technology and Innovation, and it is a profound honor to join you today at the opening ceremony of the International Year of Quantum Science and Technology 2025. On behalf of the Minister, the government and people of the Republic of Ghana, I extend our deepest appreciation to UNESCO for the international scientific community and all our partners for championing these groundbreaking initiatives. Today marks a historic milestone for global science and technology. Quantum science and technology stand at the forefront of 21st century scientific advancements, unlocking new dimensions of understanding in fields as diverse as physics, chemistry, biology, information science, and energy. It is a privilege for Ghana to be a central advocate for this international campaign, which aligns seamlessly with our shared aspiration to harness science and innovation for sustainable development. Ghana takes immense pride in its legacy of championing international science campaigns. The journey began with the leadership of our distinguished son, the late Professor F.K. Alote, during the 2015 International Year of Light and Light-Based Technologies. That initiative gave birth to the establishment of some pivotal projects in Ghana for which we seek international support and participation. Key among them, the upgrading of the Laser and Fiber Optics Center at the University of Cape Coast, now a fully fledged institute for capacity building, the establishment of laser medical application laboratory and the Solar Technology Research Center, and ongoing initiatives for dedicated R&D funding assistance to implement key scientific programs to fully support national science and technology agenda. Building on this solid foundation, Ghana was proud to propose the resolution for the International Year of Quantum Science in 2025 at the 78th United Nations General Assembly. This resolution garnered overwhelming support from UNESCO member states, scientific societies, and international bodies, such as the African Academy of Sciences and the International Union of Pure and Applied Physics, and many others. Excellencies, ladies and gentlemen, quantum science and technology hold transformative potential to address some of the most pressing challenges aligned in the UN Agenda 2030, from revolutionizing communication systems and medicine to providing sustainable energy solutions and climate-focusing tools. Quantum science technologies are reshaping industries and redefining the future. Ghana believes that the International Year of Quantum Science and Technology must aim to inspire a new generation of scientists, especially young women, to explore careers in this field. By fostering global collaboration in education, research, and innovation, we are laying the groundwork for a more inclusive and skilled workforce capable of driving transformative change the world over. As a nation committed to advancing scientific innovation, Ghana has taken proactive steps to support quantum science and technology. This commitment is anchored on various policy initiatives, such as the development of Ghana's STI for the attainment of the Sustainable Development Goals Roadmap, the review of our national science and technological policy systems, the Science, Technology, and Innovation Capacity Needs Assessment, and our quest to be an integral part of various scientific initiatives within the broader international science community, all aligned to the UN Agenda 2030, the AU Agenda 2063, and the STISA 2024. We recognize the potential of quantum science and technology to empower our youth, bolster our economy, and enhance our ability to research capacity in quantum technologies, and we are determined to deepen these efforts through international partnerships and knowledge exchange. Ladies and gentlemen, the International Year of Quantum Science and Technology presents a unique opportunity for the global community to unite behind a common vision. Let us commit to making quantum science accessible and impactful for all, ensuring that its benefits reach even the most vulnerable populations. Ghana is proud to stand with UNESCO and our international partners in this transformative endeavor. In conclusion, as we officially launch this international year, let us be reminded of the boundless potential of science and innovation to advance humanity. Together, we can harness the power of quantum science and technology to build a sustainable, equitable, and prosperous future for all. I thank you all for your attention. Thank you very much.
Thank you, Your Excellency. Now let's welcome our next speaker to the stage for the first keynote address of this plenary. Ses recherches pionnières en optique.
Her pioneering research on ultra-short light pulses have revolutionized our understanding of light at the quantum level, allowing us to observe and manipulate electrons in atoms and molecules across femtoseconds. Today, we will take part in a journey across her incredible discoveries, and we'll hear some of her reflections on watching the quantum world with ultra-short light pulses. It's a great honor to invite Professor Anne L'Huillier, eminent physicist and 2023 Nobel laureate in physics, to present her keynote address.
It's a great pleasure for me to give a talk and opening this ceremony about the anniversary of quantum. So I'm going to talk about watching the quantum world, but I would like to try by how did it start? So there will be two parts in this talk. How did quantum mechanics start? And can we observe the quantum world? I think it started actually 125 years ago with the theoretical discovery by Max Planck in 1900. Max Planck was trying to describe the radiation from a black body, the body at a given temperature, and he was trying to reconcile the Wien approximation, which is valid at high frequency, and the formula from Rayleigh genes that you have here in red. And he come up with this law that you have here, which is now called Planck's law, where for the first time he introduced the concept of light quanta. Light is described in terms of energy quanta with this h nu term. And h is now called the Planck constant. Quantum physics has received many Nobel Prizes, and I will, so what I'm showing here is a small Nobel medal, so I will show some Nobel medals throughout my talk. Einstein, 1905, used this concept of light quanta introduced by Max Planck to explain the photoelectric effect. And I'm showing a picture, not of a metal, which was used first to show the photoelectric effect, but of an atom. So he used the light quanta to reproduce the kinetic energy that is emitted by that electrons get when a metal surface is irradiated by light. And he showed that this kinetic energy depends only on the frequency of the light. Again, he used this light quanta, and also of the, for a metal, the work function. So you need a certain threshold to get the photoelectric effect, and then you can calculate the kinetic energy this way. This was confirmed experimentally by Millikan in 1914, and he even could measure the Planck constant for the first time. And let me also mention the discovery by Einstein of stimulated emission in 1917. This is really the basis for laser, so it's a very important discovery. Again, using this concept of light quanta photons. Now I'm coming to Niels Bohr, and this is a little bit Nordic slide with both Niels Bohr, who was in Copenhagen, and also Janne Rydberg, who was in Lund. Niels Bohr was trying to explain the spectra from atoms, in particular the spectra from hydrogen, and these spectra were in form of lines. And a few years before, Janne Rydberg had found an empirical formula to describe this line spectra that you have here. So again, using this light quanta idea, Niels Bohr formulated a model of an atom, which you have here with a nucleus, very heavy, in the middle, and then electrons rotating around the nucleus on special quantized orbits. And an electron, so this was very non-classical, with the electron does not radiate energy as it rotates around the nucleus, but the electron can jump from one orbit to the other by emitting light with energy equal to the difference between the energy of the different orbits. And the frequency of the light, again, is related to this difference in energy through the formula that you see here. De Broglie, 1924, was really intrigued by the fact that now light could be both waves and particles, and come up with the hypothesis that this may be applied to matter as well, and especially electrons. And the wavelengths of, that you can associate to matter is given simply by the Planck constant divided by the momentum of the particle. And this was later verified, was shown experimentally in a very beautiful experiment performed by Davison and Germer in 1927. They irradiated nickel surface with electrons, and they observe an interference pattern that you see here. Now I'm coming to the year that that is the anniversary that we celebrate today, which is 1925, with two breakthroughs approximately at the same time. The wave mechanics, which was formulated by Erwin Schrödinger with the famous Schrödinger equation that you see here, describing particles with a wave function. And then matrix mechanics, which was formulated by Heisenberg, Born, and Jordan. And you have the using operators instead of wave function, a little bit more abstract. And you have here the equation for within wave mechanics. I think at first they did not agree with each other, but very rapidly Erwin Schrödinger showed that the two formulations were really equivalent. Max Born interpreted the wave function in a beautiful article where he said that actually what we can observe, what we know is the modulus square of the wave function, which represents the probability to find the particle certain place, certain position, and a certain time. And this is called Born's rule. Now, this quantum mechanics was immediately very successful and really opened many, many branches in physics. It opened quantum field theory when quantum mechanics was applied to field, with maybe to start with Paul Dirac that could reconcile the special relativity and quantum mechanics in 1928. And then you have quantum electrodynamics, applying quantum mechanics to the electromagnetic field, and etc. Lasers, masers, lasers, quantum optics was also a consequence of quantum mechanics in optics, with maybe to cite only one thing, the invention of the laser in 1960. And then quantum mechanics revolutionized the other branches of physics, at least the microcosmos, atomic and molecular physics, chemistry, nuclear and particle physics, and of course condensed matter physics. And now I'm showing pictures of many men. So what happened to women? They actually contributed to quantum mechanics, but maybe for historical reasons they have been at least partly forgotten. But let me at least show one picture of, I think, a very famous woman scientist, Maria Goeppert-Mayer. She both was important for my own field of research because she predicted theoretically the possibility of multi-photon processes in 1931. And of course, she was very important in nuclear physics with the shell model of nuclei. Now I'm coming to the second part of this talk. Can we observe the quantum world? And the fathers of quantum mechanics, they had doubts and questions. And let me start by Erwin Schrödinger. And this is a citation from Schrödinger from 1952. And he wrote, "We never experiment with just one electron or atom or a small molecule. In thought experiments, we sometimes assume that we do. This invariably entails ridiculous consequences." And I think one of the real progress of quantum mechanics during the century has been to really show that, yes, we can do experiments with individual quantum systems. And let me start by the beautiful work in atomic physics of Devin Waveland and others, where they managed to isolate a single ion in a trap and observe the behavior of this ion, change the degree of freedom, for example, of the motion of the ion, manipulating the state of the ion by interaction with light, for example, through a Raman process, as you see here. Another very, I think, impressive achievement was that of Serge Haroche and co-workers. They managed to isolate a single photon or a few photons in a cavity and manipulate the state of the electromagnetic field by interaction with atoms, in this case, Rydberg atoms absorbing or emitting light. Another important question from Albert Einstein: is quantum mechanics complete? And can quantum mechanical description of physical reality be considered complete? And this is the title of a very famous article by Einstein, Podolsky, and Rosen in 1935. And here's another quote by Einstein in a letter to Max Born in 1947, famous quote: "I cannot seriously believe in it because the theory cannot be reconciled with the idea that physics should represent a reality in time and space free from spooky action at a distance." And is referring here to a kind of a word property of quantum mechanics. When you have entangled pair of particles, if you make a measurement on one of these particles, it affects the state of the other particle, even if the particles are very far away. In 1964, John Bell managed to invent an inequality which allowed experimental tests of the prediction of this local realism interpretation versus those of quantum mechanics. And experiments were performed by Clauser and Friedman, Alain Spey and co-workers, Anton Zeilinger and co-workers, and many others, with increasing precision over the year on pairs of particles. And the conclusion is that the real world experiments are in agreement with the prediction of quantum mechanics, meaning that our world has a very strange property of non-locality.